So let's see if we can fill in the table. Give me a second here. Okay, so if the side length, what's the first side length? 1. Which means the perimeter is what? 4. Very good. What's the side length of the next one? 2. What's the perimeter? 8. Side length 3. What's the perimeter? 12. What are we doing each time, actually? Multiplying by 4 to the side length. Does everybody see that? 5 is 20. Some people might say we're adding 4 each time. You could say that, I guess. 6 is 24, and then 7 would be 28. The reason a square is multiplied by 4 is because a square has 4 equal sides, so that's why multiplying by 4 would work as well. Okay, let's plot this. Remember how to plot? Everybody see my scale here? My y is going up by 4s, just so you know. So 1, 4, 2, 8. Isn't that convenient that I had that scale like that? 3, 12, 4, 16, 5, 20, 6, 24, 7, 28. And is this something that I can actually connect together? Yes. So let's take a line and connect it. And would I draw an arrow at the end of this? Yes, because it would go on forever. Would I draw an arrow going the other way? No. Can you have negative lengths, people? No, we cannot have negative lengths. Okay. Why not? Okay, now we're going to talk about area. So when we have a side length of 1, what's my area of my square? 1. My side length is 2. What's the area of a square? 4. When my side length is 3, what's my area? Not 6, 9. When my side length is 4, what is my area? 16. What am I doing each time? Multiplying by itself, what's that called? Squaring. Very good. Okay, let's plot this. Notice I'm going up by 5s here. Okay, for my y. So 1, 1. So that's probably just a little bit there. 2, 4, that's almost 5. Does everybody see that? 3, 9, well, that's almost 10. 4, 16, that would be a little bit past 15. Does everybody see what I'm doing there? 5, 25, so 5, 10, 15, 20, 25. 6, 36. 5, 10, 15, 20, 25, 30, 35, and a little bit more. 7, 49, so that'd be a little bit less than 50. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, so just a little bit less. Now, does this make a line? No. Would the area of a 0 side have 0 area? That would be yes. So we're going to start here, and it looks like a curve, like that. And it goes on forever that way. How are the two graphs the same? To the right, yeah. So that's called increasing functions. If they're going on forever to the right. How are they different? One is a line, so that's called linear. One is linear. I'll put a line. The other is not, you could say, or you could say is a curve. Now, if the function had negative numbers, we're talking about length, so there was no negatives, but what would happen if I were to continue this with negative lengths? Would it go down further to the left? Raoul says it would go back up, and he was absolutely correct. And why would it go back up? Yeah, negative times a negative would be a positive, so then it would be going in, it would increase that way. But if we read it from left to right, it's actually decreasing and then increasing. So the above two graphs are the same in that they both deal with squares of different lengths. One graph shows the perimeter of a square as a line. The other graph shows the area of a square, which we see as an increasing at a faster rate. How do we compare these two graphs mathematically? The perimeter graph shows a linear function. Linear.
Linear. L-E-A-N-E-A-R.
Fine. So the perimeter of the graph shows a linear function. This means that there are no exponents in the equation. Like, for instance, a line, y equals mx plus b, y equals 3x plus 1. Yes? Let's go back to the line. Can anybody tell me what this line is? I'm sorry? It would be y equals 4x, yeah. Very good. Okay, so the area graph shows here's a new term, quadratic function. This means there is an exponent of 2 in the equation. For instance, y equals x squared. That's actually what we graphed, was y equals x squared. Y equals 3x squared minus 4. So the general form for a quadratic is ax squared plus bx plus c equals 0, where a cannot be 0. How come a cannot be 0? Anybody? What happens if you make a 0? Then that x squared goes away. And then what kind of function would we have if we just have bx plus c? A linear. Yes. Does anybody remember what type of degree this is? This is going back to grade 9 math. What degree is this? Degree is the highest power of the variable in the equation. So this would be a second degree equation. This is called the general form of the equation of a quadratic. Some other examples would include, we could have y equals 3x squared plus, I don't know, 5x minus 1. Here's another one. Y equals 2x squared plus 5. That's a quadratic. It just doesn't have a middle term in it. B is 0 in that case. I could even have y equals negative 5x squared and not even have a b or a c in it. The only thing that it has to have an a that's not 0. Okay, so we're going to see what an actual quadratic looks like by using a table of values. But once we get to know what it looks like, we're going to try to do this without a table of values afterwards. So, table of values. If x is 3, what is y if the function says take your x and square it to get your y? It would be 9. What about 2? 4. What about 1? 1. What about 0? 0. What about negative 1? It'd be positive 1. Why is that? If I square something, that means negative 1 times negative 1, right? That would be positive. Negative 2, the whole thing squared. Positive 4. Negative 3, the whole thing squared. Positive 9. Let's plot this. In order to get full marks when you're graphing, you need to label the x and the y-axis, and you should have a scale. So, sometimes our scale is not given by ones. I know a lot of times in the past, you would just assume it's going up by ones, but we actually get a half mark deduction if we don't say the scale. So the easiest way to say a scale is put a 1 there and a 1 there, and that's good enough. Now I establish it's going up by ones. So 3, 9. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 4. 1, 2, 1, 2, 3, 4. 1, 1. 0, 0. Negative 1, 1. 2, 4. 3, 9. How did I do the left side so fast plotting? Yeah, it's a mirror image, and that's what you should do. From now on, if you get one side of the parabola, it's actually called a parabolic shape, so it's called a parabola. If you get one side of it, you can just mirror it on the other side. That's the beautiful thing about a quadratic. It's always a mirror image. So do not take a ruler now. We're going to do a nice curve. So kind of get your arm flowing and kind of go down and back up. There's what a beautiful parabola looks like. It's not a U. It's not a V. It is, if you cut off the parabola, say at the bottom, it kind of looks like a V or a U. But the thing is it increases faster at a faster rate. Okay? The shape of the graph of a quadratic is called a parabola. So yeah, a parabola always has a mirror image. If you take some physics and they talk about parabolic shapes, again, it'll be the shape sideways, say on a light of a car. Okay, P-A-R-A-B-O-L-A. I'll make my R a little bit better. Okay, now we're going to graph this one. This one takes a little bit more math involved. I would highly recommend doing 3, 2, 1, 0, negative 1, negative 2, negative 3. Or you could go negative 3 all the way up to 3. It's up to you. Okay, so I'm going to show my work here because I know somebody's going to say, whoa, 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 how did you get that number? So y equals negative. Then I got a 3 that's squared plus 2 times 3. Does everybody see what I'm doing for my 3? What do I do first? Do I apply the negative or the square feature first? This square. So if I square 3, what do I get? 9 with a negative stuck in front of it. Then I got to do this, multiply, and I get plus 6. And then what do I get as my final answer? We should not be using a calculator for this. Negative 3. 2 goes in. We square it, we get a 4 with a negative stuck in it, and then we have, maybe I should show my work again. It's negative, then it is subbing in a 2 squared plus 2 times 2. Does everybody see the negative is not the squaring? It's not saying negative x the whole thing squared. It's not saying that. It's saying square it first, then stick a negative in there. Okay? So we're going to square this. So we get negative 4 plus 4. So what do I get? 0. 1 goes in there. How about you guys complete the rest of the chart for me? And I'll give you a moment to do that. Is that what you got for your chart?
Yeah.
Okay, let's plot this then. So, my y and my x labeled, and put my scale 1, 1. 3, negative 3. 1, 2, 3, negative 3, 1, 2, 3. 2, 0. 1, 1, 0, 0. Negative 1, negative 3. Do you see? There's the second part of the mirror. Now we're getting new stuff on the other side. So then we get negative 2, 1, 2, 3, 4, 5, 6, 7, 8. I can mirror it on this side even though I don't have a point for that. And then minus 15 is off the chart, so I'm just going to use that to get my shape. There we go. Did everybody see what I did? I mirrored the other side. Once I got -2, -8, I put it on the other side. Makes a beautiful shape. Is yours a beautiful shape like that? Oh yeah? Okay, so here's some characteristics about parabolas. The blank of a parabola is the highest or lowest. It's called the vertex. The vertex may be if it's a highest point, what do we refer to it as? What would that become right there? What would that be? The highest point. Starts with an M. Maximum. And in the previous example, that went to a low point. What do you think that would be called? A minimum. The blank intersects the parabola at the vertex. This is called the axis of symmetry. Remember, we noticed right away that there was a mirror image on either side of the high point or low point. That would be called the axis of symmetry. Basically, if you remember back in grade 9, and I don't know if you used a mirror or whatever, but you can put a line. Essentially, I'm going to use a different color. I'm going to use a dashed line just to show this is my axis of symmetry. Meaning on the right of this green line is the same as going on the left of the green line. Okay? The parabola is symmetrical. And this is key about this line. If you make a parabola and it doesn't have that nice symmetry to it, you either calculated a coordinate wrong or you graphed something wrong. It should always have this nice symmetrical symmetry to it. Now, what made my parabola turn upside down in example 2 versus right side up in the first example? Yes. When the coefficient of x squared is positive, we'll say a plus, the parabola opens, we say up, and its vertex is at a minimum point. When the coefficient of x squared is negative, the parabola opens down, and the vertex is a maximum point. Does everybody see? If the coefficient is positive, if we're positive, usually we have happy faces, the parabola opens up. If we're negative, we're usually got Mr. Grumpy Pants there, and we're got the parabola opening down. Good way to remember it. Especially with all you guys using all your emoticons all the time.
That may not have happened with the sub here.
Okay, so let's carry on. The blank of a quadratic function is all possible x values. What do you think I'm talking about there? The domain. Does everybody agree that there is no limitation to my x values? I can plug whatever I want in there. The domain is everything. So the domain of all parabolas is x is an element of the reals, or how do I write this in interval notation? Round bracket, negative infinity to positive infinity. The blank of quadratic is all possible y values. So what am I talking about there? Range. Now, the range is not all y values, it's all possible y values. So it depends whether it's going to, the parabola opens up, and if it opens up, it's a minimum to infinity. If it opens down, it would be negative infinity to the maximum. It all depends on the position of the y value of the vertex. Does everybody agree? Again, I will show you just a visual. Here is an opening down one. Does everybody see it's going from negative infinity all the way up to wherever that maximum value is? And if it opens up, it's going from that minimum value all the way up to infinity for the range. But the domain is everything, right? Even though the parabola looks like it's not getting too far to the right, it actually is. If we could draw a parabola big enough, you would see it's going on and on and on. The x-intercepts of a graph of a quadratic function are called the... I don't know if you know what this term is right now. Is called the roots. The x-intercept is called the roots of the function because they are the values of x when the function is blank or y equals blank. What am I looking for there? Okay, where the function is 0 or y equals 0. Function value f of x is simply a fancy name for y. I actually have a poster in my room at the back that says that. Function notation is just a fancy way of writing y. So remember that. Some x-intercepts are also referred to as, and you might not know, solutions. So x-intercepts, roots, and solutions are all the same thing. We're referring to where it crosses the x-axis. Everybody got that? Okay, moving on. We have a summary of what we just learned today. So I'll give you a second to see if you can draw and make a description of what these are. We have lots of time left. Okay, so vertex, let's draw a diagram. So we could draw, here's your x and y axis. You can have a parabola anywhere, right? And what is our vertex? Our vertex is either the minimum, or if you draw it over here, you could have, I don't know, say a maximum over here. So what's the definition? Yeah, the highest or lowest point in parabola. Everybody know it's an actual coordinate? An example. I don't know, it might be a hard time. Did everybody do this in science class where you had like a concept map? Yeah, you've done this before. What could be an example? I don't know, you could say y, we could use one of our other examples, y equals x squared, and the vertex is at 0, 0. Okay, axis of symmetry. Some people are having trouble remembering what I meant by that. If I have a parabola here and here's my vertex, oh, that's a bad drawing. I'll try that again. So if I have my vertex here and it looks like this, my axis of symmetry, I'm going to draw it as a dashed line. This is my axis of symmetry. And what is it? It's the line that goes through the vertex and splits parabola into two equal parts. Something like that. And does anybody know what an example, if this coordinate right here, I'm just making this up, that this is 3, 2, what would the axis of symmetry be when the vertex is 3, 2? What's the vertical line that goes through 3, 2? Rylan, it's not just 3. You have to say something else with it for it to be an equation. Something equals 3. X equals 3. Okay, I don't know if you can read x equals 3 here. Intercepts. Intercepts refer to both the x and the y-intercepts. So that is where it crosses the x-axis and the y-axis. So the x-intercept is where graph crosses x-axis, and the y-intercept is where the graph crosses the y-axis. It's a value, it's not a coordinate, even though it is a point. When I ask for the x-intercept, it's a value. So for instance, if this is my parabola here, I don't know, we'll just kind of go like this and like this. This is say 1 and say 3. This is say 2. So my example would be my x-intercepts are 1 and 3 and my y-intercept is 2. Domain and range. What's the definition of domain and range? Yes, domain is the inputs or the x's, the x values possible. And the range is the output of the function or the y values that are possible. Okay, so for instance, say I graph this parabola here. I'm going to put it over here this time. It's going to go like bada bing, bada boom there. And it's going to be, say, -2, 3. What would my domain be for my parabola? What would my domain be? This is like the easiest mark you ever get. I don't actually even give a mark for it because it's always, the answer is always going to be -infinity to +infinity. And what's my range? Well, when the parabola is opening down, it's going to have a maximum. So what's the lowest point? -infinity going up to, what's the highest? 3. Does it include 3? Yes, so that would be a square bracket there. All right.